All right. So let's look at the third lecture on the stack abstract data type, and let's look at one more application of the stack abstract data type. Recall that in the last lecture we uh, looked at using stacks for checking for balance parentheses, and we also saw at the end of the lecture that it was not a toy programming exercise. It's a very, very important programming exercise. I showed you the editor that I use on my computer that highlights matching parentheses, and we essentially wrote almost that whole program. In today's lecture, what we are going to do is we're going to look at expression evaluation. Right? So we're going to see that expression evaluation, which involves precedence of arithmetic operators, is fairly sophisticated if one has the expression in the format that we are comfortable with. This is the infix format, where for every operator, the operands occur to the left and right respectively. For every binary operator, the operands occur to the left and right respectively. So we have very sophisticated precedence rules there, especially when there are parentheses. Right? So most of you will recall that there are these rules called board mass rules, which tell you in what order you must evaluate sub-expressions to be able to correctly evaluate a given expression. Now, we'll also see that if the expression is given a slightly modified form, then the expression evaluation rule becomes very simple. Right? And therefore, the challenge is going to be to convert the expression from a given form, which is the infix form, where the operators are preceded and succeeded by their operands. Right? Conversion from this format to the simpler format, which I call the postfix, is going to be a very interesting programming exercise. So that is the focus of today's lecture. So we will spend about, again, 20 minutes on this exercise, 20 to 25 minutes on this exercise, where we will look at the slides to describe the programming exercise and then quickly go to the program that I have written. All right, so we are interested in looking at mathematical calculations, like I said. For example, we can ask this question: what is 3 plus 2 multiplied by 4? What is 2 multiplied by 4 plus 3? And what is 3 multiplied by 2 plus 4? And if we do not have a uniform convention about which operators will be evaluated first, then one can get different answers. For example, let us look at this simple one. Right? Most school children are likely to think of this as 5 multiplied by 4. That is 3 plus 2 multiplied by 4. If you ask a third standard kid who understands a bit of arithmetic, the child is very likely to tell you that it's 5 multiplied by 4, which is 20. Right? But the minute we put in the conventions of the precedence rules, then the answer we all know is actually 11. That is, the multiplication needs to be done first and followed by the addition. Right? So that is, this multiplication needs to be done first, followed by the addition. This can get even more complicated in the presence of parentheses, but before that, right, we can have also other binary operators like exponentiation. Recall that exponentiation is a binary operator, right? 4 to the power of 5. Similarly, here you see 7 to the power of 2 to the power of 2. Right? Now, right, so this is 7 to the power of 4 basically. Right? And these are all, so we need evaluation rules, right? So for example, exponentiation has the highest priority, followed by multiplication and division, but multiplication is done first, followed by this multiplication, followed by this division, right? So therefore in the denominator will be 7 to the power of 4, right? And this exponentiation is also done first, right? And so on and so forth, right? So therefore, how does one represent the expression so that the precedence rules can be easily checked? Now, what is the problem? The problem is that the two operands that occur to the left and right of an operator are not directly available from the expression. In other words, because of our precedence rules, if you ask what are the arguments, what are the operators for this minus sign, what are the operands for this minus sign, we know from our evaluations that it is the result of 1 minus 2 followed by the result of this whole expression. Right? So it's really 4 power 5 multiplied by 3 multiplied by 6 divided by 7 power 4. Right? The result of that is subtracted from the result of 1 minus 2. Therefore, that is what is brought out in this point. We say that for every operator, the two operands which occur to the left and right are not immediately available. For example, when I mean immediately available, for this minus you cannot say the operands are 2 and 4 respectively. You can only say that it is the result of the expression 1 minus 2 and the second operand is the result of this very complicated looking expression. Therefore, how does one extract this information is the challenging question. So now the question is, can we rewrite the expression so that we can get an equivalent expression in which the operator follows the two operands, right? So therefore, let us just see this, right? So is it possible to rewrite the expression so that in a simpler form, that is whenever you see an operator, the immediate two symbols preceding it are essentially the operators, are the operands, I'm sorry. So let me restate the sentence again, right? Is it possible to rewrite a given expression, that is a given expression in this form, in an equivalent format where every operator follows its two operands, right? Such a notation is called the postfix notation. The notation that we are used to from school days is called the infix notation. Right. So let us look at a few examples of the infix and postfix expressions. Right. Let us look at the postfix expression 3, 2. These are the two operands, followed by star, followed by 1, followed by plus. Right? So now this is the postfix of 3 star 2 plus 1. Right? So the postfix expression really has no precedence. All that you have to do is read the expression from left to right. Whenever you see an operator, take the two operands and evaluate it. Right? And we'll see how to do this in a short while, but the rule is very simple. Whenever you see an operator, you pick the two operands that occur just before it. Right? For example, you may be confused to find out what are the two operands for this plus. One operand is 1. The second operand is obtained by evaluating the star. Right? What are the operands for this star? It is 2 and 3 respectively. Therefore, the operand for this plus is 1 and 7. Sorry, 1 and 6. Therefore, the result will be a 7. And so on and so forth. Therefore, let us go through the rules for evaluating a postfix expression. We just saw this. Let's do another one here. Let's look at 1, 2, 3, 4, exponentiation, star and plus. Okay. So let us scan the expression from the left to right. So you see 1, 2, 3, 4, exponentiation, star, plus. Right. So now when you see the exponentiation, right, what are the two operands for the exponentiation? 3 is the left operand and 4 is the right operand. So you see 3 to the power of 4. Right? So therefore, you will see 3 to the power of 4 now replacing this fellow. Now you see a star. What are the operands for star? The right operand for star is 3 to the power of 4 and the left operand is the 2, as you see here. Finally, you see a plus. The two operands for plus are the right operand is the result of 2 multiplied by 3 to the power of 4 and the left operand is a 1. Therefore, evaluating postfix seems to be fairly simple. So let us first look at a few examples for evaluating postfix expressions, and following that, let us see how to convert from infix to postfix. Right. So evaluation of postfix expressions is very simple. We will do this using a stack. Given a proper postfix expression, we get the next token, which is the next symbol. Right? I call this a token because when you look at a program and if you are identifying the order in which expressions must be evaluated, the variable may not just be a single symbol, but it may be a combination of multiple symbols. Okay? Now, if it is an operand, right, that is if it is an arithmetic if it is an operand, you push it onto the stack. If it is an operator, you pop the stack first to get the right hand operand, then you pop the stack to get the left hand side operand, and you apply the operator on the two operands and push the result back onto the stack. And when the expression is being done, whole expression is exhausted, the result will be at the top of the stack. So let's go through this again. You parse or you go through the whole expression from left to right. Whenever you find an operand, you push it onto the stack. If you find an operator, pick the two operands from the top of the stack, perform the arithmetic operation, push it back onto the stack. Repeat till the whole expression has been processed. That will essentially give you a way of evaluating the postfix expression. We'll definitely look at a program which does this, and let us look at now the challenging exercise of converting an infix expression into a postfix expression. For example, let us look at the infix expression 2 power 3 power 3 plus 5 star 1. Right? So clearly what are we supposed to do? We are supposed to take 2 power 3, which is 8, and 8 to the power of 3. Right? And then add it to the result of 5 multiplied by 1. This is the application of the precedence rules. Right? So this is the infix expression for this postfix expression. Fine. So now let us just see whether we get exactly the same procedure, right, or this expression when we apply the algorithm that we saw on the previous slide. Right? So we push 2 onto the stack, 3 onto the stack, then 3 onto the stack. Then exponentiation comes, right? So when exponentiation comes, we take the previous two operators, which is now gives us 3 power 3, and which is to write it onto the stack. And then we consider 2 power 3 power 3. And then we get to compute the product of 1 and 5, and then we get to add the whole result. Right? Similarly, you can see that this is the infix of this particular expression. The key issue here is that somehow in the conversion of the infix to the postfix form, the precedence of the operators must be somehow enforced. Right? And we also will have to come up with a method to deal with parentheses in the expression. Before that, before we go to the program, let us look at a simple example. Right? Let's look at the example and then we will come back to the. So here is the infix expression 3 plus 2 star 4. Let us look at the postfix expression on the operator. Right. So the operand comes, now we write it into the output postfix expression. Now the operator comes, it is pushed onto the stack. Then another operand comes, we write it into the expression. Then we push the next operator onto the stack. Then we print out the last term, and then we pop from the stack while it is empty. So that was just a very simple example, and let us look at the complete algorithm for achieving this. We will exactly implement this piece of code that you see here in the C program, which we will see shortly. So here what we do is we maintain the operators in a stack. Whether to push the operator onto the stack or pop from the stack depends upon the precedence with respect to the operator at the top of the stack. So let us just understand this. When I see a certain operator, to decide whether to push onto the stack or pop onto the stack depends upon the precedence with respect to the operator at the top of the stack. So we will see this rule in a short while. The operands, whenever we see an operand, we send the operand to the output postfix expression directly. Now let us look at the parenthesis and the operators. The first rule is when you see an open parenthesis, you push it onto the stack. When you see a closed parenthesis, you pop all the stack symbols and print it out one after the other. Remember, the stack symbols are all the operators. You pop them all out until an open parenthesis appears, right? And you pop the open parenthesis and print it out. When you see an operator, the rule is as follows. You pop all the stack symbols until the top of the stack consists of an operator of a lower precedence. Then you push the operator onto the stack. Let's go through this again. When you see an operator, you pop all the stack symbols until an operator of lower precedence is obtained at the top of the stack. Right? When you see this operator of lower precedence, you then push this operator onto the top of the stack. Understand what we are seeing? When you see a certain operator, right, what we are basically saying is that we'll perform on the stack all the operations of higher precedence first, right, and then we'll perform this operator, and then we will perform an operator of the lower precedence. That is the idea here. So you pop all stack symbols until you see a symbol of lower precedence. Right? Then you push the operator onto the stack. Anyway, whenever you pop anything, you print it into the output postfix expression. At the end of the input, you pop all the remaining stack symbols and add it to the expression. So this is the whole idea of the infix to postfix conversion algorithm. Right? So observe this. The input expression, which is an infix form, has three kinds of symbols: operators, operands, and parentheses. Whenever you see a parenthesis, open parenthesis, you push it onto the stack. When you see a closed parenthesis, you push all the operators on the stack. You pop all the operators on the stack till you see a open parenthesis, which also you will pop out. And of course, you never print out. I have not written this here. That was a small mistake on my side. Remember that we will never print out the parenthesis in the postfix expression. The postfix expression contains only the only the operators and the operands. It does not contain any parenthesis. When you see an operator, you look at the operator and then you pop all the stack symbols until you see one of lower precedence at the top of the stack. And then you push the operator onto the stack. And whenever you pop an operator, you pop it out into the output postfix expression. And whenever you get an operand, you directly send it into the output postfix expression. So this is the whole algorithm. Right? And I encourage you to run this algorithm on the different examples that we have seen so far. Let's go to the program which implements the infix to postfix converter. This is called in-to-postfix.c. Okay. So the first one is to check if the character is an operator or not. This is a very crucial thing, and these are the operators. Right? Otherwise, we assume that it is an operand. Right? Okay. Then we also have the precedence rules. Right? So what is the precedence of C? Right? So we use a switch function. If plus and minus, you see they have the least precedence. Right? So we give them the precedence which is 1. Star and division are seen, they give the precedence 2. Right? And if the exponent is seen, it has the highest precedence, it is of precedence 3. Right? Otherwise, the precedence is -1. This is to handle the open parenthesis case. So now here is the infix to postfix converter. Okay, sorry for the cleaning up operation. This is just to make the code more readable. Okay, so what do I do? Expression, and recall that the expression is an infix. So exp has the expression in infix, right? And the number of symbols as is size, right? So now you create a stack of size. Observe that we actually don't use the whole stack when we create a stack which is of same size as the size of the expression. We actually are creating a stack which is slightly larger. So what do we do now? Right? So we create a stack of that particular size. Right? Recall that we are going to use array implementation of the stack. Right? So therefore we'll get an array which stores this whole expression, and here is the output, right? Which is going to be a character string, right? And it is going to have size plus 1 locations, right? One additional location to store the null character. Okay, so here are the rules. If the symbol that is read is an expression, right? So while the operators are not empty, right, and the precedence of the operator that you see at the top of the stack is greater than or equal to the precedence of expression of I. That is, as long as you see operators of precedence which is larger, you keep popping. Right? And where does it go? Whenever you pop, it goes into the output. Right? So it goes into output of k, which is initialized to 0, then you increment the counter, then you pop again. Right? And when you exit, what is the condition for exiting? You exit either when the stack becomes empty, or the operator that you see at the top of the stack is of precedence which is strictly smaller. At this point, you push your operator, right, onto the stack. Otherwise, you now check if it is an open parenthesis, in which case you blindly just push it onto the stack. That is, push onto the operator's stack. On the other hand, if it is a closed parenthesis, now what you do is, while the operator stack is not empty and you don't see a open parenthesis, okay, you take the top of the stack operator and then push it into the output stream. Observe that I could have written actually, well, pop is a function that does not return, right? So pop is a function that does not return any value, right? Right. So we read the value, write it into its location, and then we pop it off. Right. Observe that there is a bit of program design here. Right. We have designed it so that pop does not return any value, whereas peek returns the value which is the top of the stack. Okay. So you keep popping till you see the open parenthesis. And when you see the open parenthesis, you pop the open parenthesis on the stack. Otherwise, what do you know? You know that it's not an operator. You know it is not a parenthesis, open or closed. Right? Therefore, it must be a operand. Right? Of course, you must be careful when you use this function. I mean, if I give you a meaningless symbol, your formula may not be evaluated. Now you go to the next symbol. You repeat this procedure till the whole expression has been processed, right? Till I is less than size. Now what you do, while the stack is not empty, right, you just keep printing out the operators which are at the top of the stack, that is, keep sending them to the output. Right? Finally, you put a null symbol so that output becomes a string. Now you return output. I also have another small function which is to evaluate a postfix expression. The input is given, right, as a character array of a certain number of elements. Now we create a stack of a particular size. Right? This stack is going to store the value. Right? Observe that this particular program contains two functions. One is that it evaluates a postfix expression. The other one converts an infix to a postfix expression. Okay, so now we have a result stack. The stack has size number of elements in it. You initialize I to 0, and now while I is less than size. So what do we do? Right? So we look at the expression, we look at the character that we see from the expression, we check if it is a digit, right? Is digit is a function, right, which is there in the limits.h. Sorry, it is in the it is a string or the C type .h library header. We'll look at it just after this lecture as to which library header has this, right? So you check if the character is a digit, right? And if it is indeed a digit, you push it onto the stack, right? What do you push onto the stack? You push the corresponding number, right? So you take this character, subtract it from the ASCII value of 0, right? And we push it there. Otherwise, you look at the top of the stack, right? That is the first argument, right? Then you pop it. Then you look at the next top of the stack. That gives you the second argument, right? And do this. And now you do a switch, right? So if you see that the expression is, if you see that this expression is a certain operator, right? So if it is plus, then you push onto the stack the result, which is the sum of the two values. Then you exit. If it is subtraction, you perform the subtraction, push it onto the stack. If it's multiplication, you perform the multiplication and push it onto the stack, and so on and so forth. And if it is exponentiation, we do the power function. This is a library function which is in the math.h library. Then we move on to the next symbol. At the end, the whole expression has been parsed and we return the result. This whole exercise is done on a single expression, right? So let us just see this. The expression is 1 plus 2 multiplied by 3 by 4 with parenthesis, the whole thing raised to the 5 minus 6 multiplied by 7 plus 8 minus 9. Right? And then we make the appropriate functions. Output, for example, contains the infix to postfix conversion. Right? We use this string length function to give the next argument, which tells you the size of the stack. Then we print out the infix to postfix converted. Sorry, we print out the infix expression, then we print out the postfix expression, and then we print out the answer after evaluating the expression on a certain value, and in this case the value is the length of the output itself. So let us just run this program. Okay, so the input in fix format is exactly what you had seen earlier. It's 1 plus 2 multiplied by 3 by 4 whole power 5 minus 6 multiplied by 7 plus 8 minus 9. Let us look at the output. Right? So the output in postfix form. So let us just see if we can. So 1 goes into the output stream, plus goes onto the stack, then 2 gets printed out. Multiplication comes, multiplication has higher precedence than plus, so this goes onto the top of the stack. Right? Then the parenthesis goes on the top of the stack, then 3 goes onto the top of the stack. Now division is seen. So division compared with open bracket, which is at the top of the stack. So division goes onto the top of the stack, then 4 goes onto the top of the stack. Now we see a close parenthesis. We print out the division which is at the top of the stack, then we pop off the open bracket. Right? Therefore we printed out the division. Then we see exponentiation. Exponentiation has higher precedence than star, so we push it to the top of the stack. And then 5 gets printed onto the output stream, right? And so on. Right? So basically you will be able to work this out by hand to check that the output expression is indeed correct. And let us check that the size of this array is actually 17. So there are 1 to 9 are there. then the number of symbols is that between any two consecutive numbers there is one additional symbol, right? Therefore, and there are two sets of parentheses, so you will actually see that the size of the string is actually 17. The size of the input expression is 17, right? And therefore on evaluating it you get minus 98. So this is an easy exercise to work out by hand. So let us just go back to the program for a minute. So this is the function. It has two functions, one to convert infix to postfix, the other one to evaluate a postfix expression. So we have an operator function, we have a precedence checking function. Then we have a conversion from infix to postfix, which carefully takes care of the precedence of the operators. And then we evaluate a postfix expression on a given value. All right, so that completes two more applications of the stack data type. Right? So you would have seen that it's fairly sophisticated application, especially the conversion from infix to postfix is a very interesting application, taking care of precedence and implementing the precedence rules by making careful checks with the values on the stack. The values on the stack, remember, are operators. So therefore, what we've done this week is to look at the stack data type, and we will give out one programming exercise which involves using the stack data type, right, in a couple of days' time. So hopefully the lectures were enjoyable and the programming exercises will make you stronger. So keep programming and have fun.